All right, welcome back, guys. We're going to be starting chapter 6, and we're going to cover section 6.1 today. So, this chapter 6, guys, is on what are called confidence intervals. Okay, so the reason we'd be interested in this is because let's say that you're trying to figure out the mean, the parameter for some population, like I think an example that's used here in the notes. Let's say you're trying to figure out what the average height of all adult U.S. women is. And of course, you can't measure every single U.S. adult woman. That would be impossible, right? So we have to rely on a sample to try to give us an idea. And so you take a sample and you find the mean of that sample. Well, that mean is probably the mean from the sample, x bar, in other words, is probably not going to be the same as the actual average height of all U.S. adult women, okay? So when we get a statistic, guys, and that's what x bar is, when we get a statistic, there are many things that affect its accuracy. First of all, and we've talked about this, how robust is the sampling methodology, the size of the sample. The larger the sample, the more accurate the estimation. But in any case, unless we can, sample the entire population, if you will, we cannot be 100% sure that sample statistic is the actual average of the population, okay? And so we create what's called a confidence interval, okay? A certain range of values within which we assign a certain level of confidence that the true mean of the population lies, okay? And it doesn't have to be the mean, it could be like the standard deviation. But anyway, all right, so let's look at these learning objectives. We're going to find a point estimate and a margin of error. So we've actually already worked with a point estimate. That's what statistics are, essentially. They are point estimates, or they're estimates of the values of certain parameters related to a population, okay? But with each of those estimators, there's going to be a margin of error, okay? There's always some uncertainty because we're relying on a finite sample. And then we're going to construct and interpret confidence intervals for a population mean. So we're going to be interested in estimating the mean of a population just by using a sample, okay? Just by using the mean from a sample. Whenever sigma, or the standard deviation of the population, is actually known, okay? So this is a bit unrealistic in a way, because if you know the actual standard deviation of the population, then you could probably know the mean of the population. But anyway, and then finally, how to determine the minimum sample size required when estimating the population mean, okay? So for example, if I want to make sure that my sample mean is, I have a certain degree of, or I want a certain degree of certainty associated with the accuracy of my sample mean, then how big does my sample need to be so that I can ensure that accuracy? Because, guys, think about this. If you take, let's say we're trying to estimate the average height of a population. If I only sample 2 or 3 people and find the average of that sample, that's not going to be very accurate, probably. But if I end up sampling 100 or 1,000 or, say, 50,000, then the larger the sample, the more accurate that statistic is going to be at estimating the actual value of the parameter, okay? And that's what statistics is all about. All right, well, let's look at some definitions then. So a point estimate is a single value estimate for some population parameter, okay? So for us, it's going to be the sample mean. It's an estimator for what the actual population mean is, mu, in other words. The most unbiased point estimate of the population mean, mu, is going to be the sample mean, or x bar, okay? So for example, well, this is what I was talking about. If we want to know the average height of all U.S. females, we would start by taking a sample of U.S. females, we'd measure their heights, and then we'd calculate the average. And then the sample mean, x bar, would be our point estimator for whatever the true population mean is, okay? And then inevitably, though, guys, like I was telling you, our point estimate is not going to be exactly equal to whatever the population parameter is. And the difference between our estimator and the actual population parameter is what we call sampling error, okay? So you can see here, it's the mean. It's going to be the mean of our sample minus the actual mean of the population. And every single estimator, or, you know, I could take 10 different samples and I'd get 10 different averages. Well, every single one of those is probably not going to be correct. To every single one of those, there will be a certain level of sampling error. They're going to miss the mark. They're going to, you know, underestimate the true average or overestimate the true average. So, all right, well, let's look at example 1 here. It says in a survey of the heights of 30 U.S. women, the average height found was found to be 66.47 inches. If the average height of all females in the U.S. is 65.45 inches, find the sampling error, okay? Well, you know, just using that same formula from above, the estimator, or our sampling mean, is 66.47 inches minus the actual mean of the population, which is 65.48. And I want to say this is going to be 0.99 but inches. I'm going to check it in my calculator if I can turn it on. All right, yeah. So, and this technically would have a unit. It would be inches. Okay, that would be the sampling error. And then if you took another sample of 30 U.S. women, that particular sample would have its own mean, and it would have its own associated sampling error, okay? All right, well, let's continue. Okay, so why confidence intervals then? Well, because of the sampling error, okay? Any point estimate's always going to have some level of some degree of sampling error. So we use something that we call a confidence interval to make statements about what the population parameter actually is, okay? Guys, you see this, you're probably aware of this whenever you hear a political poll. So at the time of this recording, we've got an election coming up. And, you know, if you listen to the news, the world news or whatever, they say in this particular state, Donald Trump or Kamala Harris is polling at, 46%. And then they will list what the margin of error is. So that margin of error creates a confidence interval. So if somebody's polling at 46% and the margin of error is 3%, then that means it's essentially the percentage of the population in favor of that candidate's probably somewhere within 3 percentage points from that 46%. So it could range from 43 to 49, okay? And we have to use an interval because of the inherent uncertainty in relying just on the sample statistic to estimate what that true population parameter is, okay? Anyway, it says a confidence interval is a statement that looks like this. we are 95% confident that the population mean for the heights of all U.S. females is between 65.36 and 67.58 inches. This right here is a confidence interval. Okay. Now on the news, they don't typically tell you the degree, or how should I put that? They don't typically tell you the certainty of the confidence interval, so they don't associate a certain probability with it. And so typically 95% is used, although sometimes 90% is used or 99%. It just depends on how confident you want to be. Now, I will say that as you want to be more confident, the width of the interval will extend, okay? And as you want to be, I guess, less confident, the width of the interval will actually narrow, okay? So if I wanted to be 99% confident in the width, that the true population height of these women was in some interval, this interval is probably going to be a little wider to account for that increased certainty that I want. All right. Okay, well, let's continue. Okay, so how do we actually construct one? And in this particular section, we are assuming that sigma, or in other words, the population standard deviation is known. Okay, don't confuse this with lowercase s. That represents the sample standard deviation. Those are distinct. Okay, so it says first we determine whether the population standard deviation is known, and in this section it will be. In the next section it will not be. And so we have to use another method to come up with a confidence interval. All right, and then we decide on what's called a level of confidence. Okay, so this is essentially this 95%. How confident do we want to be? And then we find the corresponding, what are called critical values. Okay, what this means, guys, is we find these z-scores under the standard normal distribution such that we have this level of confidence in between those values. So we got some practice doing things of this nature back in chapter 5. I'm going to talk more about this though here in a minute. The level of confidence is typically denoted with lower italics, lowercase c. It's the probability that our interval estimate will actually contain the population parameter, assuming that the estimation process is repeated a large number of times. So you can sort of think about it, you know, in this example up here, you can sort of think about it like 95% of the time, the true population mean will fall within this interval, okay, right here. As you take more and more samples, if you were to take like 100 samples, then 95 of those would actually fall within this range. That's technically what it means to be 95% confident. To be 99% confident or have a 99% level of confidence means that if you were to take 100 different samples and you would have 100 different means, sample means, then 99 of those would fall within this range, within this confidence interval. Okay, so it's a little abstract, I know, but all right. And then the level of confidence, similar to what I was saying up here, is going to be the area under the standard normal curve between those two critical z-scores. And these, by the way, are going to be symmetric. Okay, you're going to have one that's negative and you're going to have one that's positive. They're symmetric because the standard normal distribution is symmetric. In the example above, we used a 95% confidence interval for the heights of U.S. females. Okay, so we could check and figure out what two z-scores would contain between what two z-scores would there be 95% of the total area? Well, we'll look at this later on, okay, because I have an example down below that shows this, or shows how to figure it out. And then once we have those z-scores, or those z-values, or critical values, however you want to refer to them, and we know what sigma is, then we will also need the sample mean and the sample size. And to find the margin of error, this is how you do it, okay? Or, well, this value, okay, well, I should have had this bullet point before this bullet point right here, but let's go to this one next. This quantity right here, guys, whatever that critical z-score is, multiplied by sigma over the square root of the sample size, this is your margin of error, okay? And so whatever your sample statistic is, to find your confidence interval, you just subtract your margin of error to find your lower bound, and then you add it to your sample statistic to find your upper bound, okay? So these confidence intervals, they're a range. There'll be a lower bound and there'll be an upper bound. The sample statistic will be right in the middle. What creates the range, though, is this margin of error, okay? So it's kind of like that example I said earlier. If a candidate's polling 46%, give or take 3 percentage points, then you subtract 3 and you add 3, and that's how you come up with your interval. All right. And yeah, familiarize yourself with this formula, okay, because we're going to be using it. Because in order to calculate a confidence interval, we have to know the margin of error. All right, and so this is another way to write it. Since capital E represents this quantity or this margin of error, okay, we can just use capital E. So it's going to be, the confidence interval will be whatever the sample statistic is, take away the margin of error, that'll be your lower bound, and then your sample statistic adding the margin of error, that will give you your upper bound, okay? All right, but let's just kind of segue into this. First thing we're going to do is look at finding critical values for these different levels of confidence, okay? So remember, C represents the level of confidence that we want to have. You can sort of think about it, just, you know, when C is 87.87, that means you want to be 80, you could say, I'm 87% confident. Never are you going to have C equals 100%, because if C equals 100%, that would imply that you actually know what the population parameter is. That's the only way you could be 100% confident. But anyway. Okay. So to find the critical values, guys, these are z-scores such that between these two symmetric z-scores we have 0.87% of the area under the normal curve, okay? All right, so let me draw a little graphic here. I'm going to draw a standard normal distribution. So I'm going to draw two marks from the two z-scores. One will be negative. Usually they'll write z sub c just to show that this is the z-score that corresponds to that level of confidence. And then over here this will be a positive z sub c. And in the middle I'd have 0.87, okay? So if you remember from chapter 5, we only need to know what one of these z-scores is because they're symmetric. So if I could find the leftmost z-score, I'll know what the rightmost z-score is. And so what I need to be able to figure out is how much area is to the left of this lower z-score. Okay? Well, if I've got 87% between these two, then that means I would have the other 13% in the two tails. And to figure out how much I have just in the left tail, I could divide 13 by 2, and this will give me 0.065. Okay, so in other words, we would be trying to figure out what is the 6.5 percentile. Okay, what's the z-score associated with the 6.5 percentile? Or in other words, what's the z-score such that we have 0.065 area to the left? And for this, if you recall, we can rely on our calculator. We can come over here to distributions, and we can do the normal CDF. Wait a minute. No, the inverse normal, right? Because this will give us our z-score. Okay, so the area that's to the left is 0.65. Here, though, you want to change these back to 0 and 1 because we're working with the standard normal distribution, not some raw normal distribution. And then you can hit enter, and this is the negative z-score. So typically in our problems we use just the positive. Okay, so I can write this as z of 0.87 is equal to negative 1.51, I believe. Yep. Oh wait, well I don't need the negative. You only need one of these, and you don't need the negative. The reason you don't need both the negative and the positive is because right up here you're going to subtract it from the mean, and down here you're going to add it to it. Okay, so that's why we just use the positive 1.5, because we end up subtracting and adding the margin of error to our sample statistic to find the lower and upper bound for our confidence interval. All right. Or you could think of it like this, that it's the absolute value of that lower z-score. Okay, remember the absolute value of something's always positive. All right, what about this one, part C? Or no, not part C, part B, but here C is equal to 92%. So a 92% confidence interval means we have 92% of the area in between our two z-scores, 0.92. So that means the other 8% would be in the two tails, which implies that I would have 0.04% in just one tail. Okay. And then I'd have the other 4%, over here in this tail. I'm going to go ahead and label this. This was 0.065 area. All right, well, guys, you'll do this one the same way. Okay, use your inverse normal function. And the area that's to the left of this z-score is 0.04. And, of course, you want to make this a positive, so this is going to be 1.75. So I'm going to say that z of 0.92, because this is a critical value associated with a 92% confidence interval, is going to be 1.75. Okay? All right, and then I told you above I had an illustration below. Well, this is it. So whenever C is 95, and this is one of the most common confidence intervals, 95%, that means you have 95% of your area in between these two critical Z values, which means you have 2.5% to the left here, okay? And that corresponding value of Z is 1.96 or negative 1.96. So guys, remember that. There's going to be like 3 or 4 critical values that you're going to be using over and over and over, because we're going to keep finding the same confidence intervals with the same level of confidence. Okay. But anyway, if you wanted to check with your calculator, you could. You go to the inverse normal function again. Oops. And the area that's to the left of this lower, anyway, never mind. It's 2.5%. And indeed, to 2 decimal places, this is 1.96, isn't it? Okay. And this is one that we're going to see a lot. So the critical value associated with a 95% confidence interval is 1.96. All right. Okay, so I even made a table for you guys in which I listed these critical values, okay? So common critical values, they're associated with, we could do like a 0.98 or 0.92, but those are not very common, guys. They would just be kind of arbitrary. Like I said, probably 95% is the most common, but these are the associated z-scores. And you can see as this level of confidence gets bigger, so too do the critical values, right? Because as these get bigger, the area in the tail gets smaller, and so we're talking about a larger interval underneath that standard normal curve. So the value of z would be increasing. All right, so now what we want to do is actually get some practice finding the margin of error. Okay, so in order to do this, we need, it looks like I left something out of the notes here. We need to, sigma should be in there. So find the margin of error for the given values. When we know the value of c, or what we want our confidence interval to be, we know the actual population standard deviation, and we know the size of our sample, okay? And so the margin of error is given by this formula, z of c times whatever the standard deviation of the population is divided by the square root of n, okay? All right, guys, well, because c is 0.95, you can look in this chart and see that that associated critical value is 1.96. So I'll plug 1.96 in here times sigma, which is 2.22, divided by the square root of n, which is 64. Okay, and you can literally just type all this into your calculator. So that's what I'll do. 1.96 times 2.22 divided by the square root of 64. Could just have divided it by 8, right? Because 64 is a perfect square. And when I do this, I'm only going to carry this out to 2 decimal places. So my margin of error is going to be 0.54. So now if you were trying to find the confidence interval, you would need to know what x bar is. You would need to know what the actual sample statistic is, and you would just add and subtract this error from it to find your actual interval, okay, your lower and your upper bound. All right. Well, let's actually find one, guys. Yeah, let's just go ahead and find one. Okay, I had thought about stopping this video, but I think I'm going to keep on. This is a sample of the heights of 30 U.S. females found, well, this is the one we did earlier, isn't it? Similar. Found a sample mean of 66.47 inches. From past studies, the population is found to be normally distributed with a standard deviation of 3.1 inches. So we know sigma. And it says to construct a 95% confidence interval for the population mean, and then interpret our results, okay? So I'm going to go ahead and write down what we know. We know C, or our level of confidence, needs to be 95%. We know sigma, or the population standard deviation. We know the sample size, n, which is 30, and we know x bar. We have to know x bar in order to find the actual confidence interval. And I'll put that unit on there. This technically should be inches as well. Alright guys, well the first thing I need to do is find my margin of error, okay? So because this is a 95% confidence interval, we're using that same. Let me actually rewrite the formula here. But we'll be using that same critical value. Okay, so this will be equal to 1.96 times 3.11 divided by the square root of our sample size, which is 30. And let's see what this gives us. So 1.96 times 3.11 divided by the square root of 30. All right, so I'm going to call this, I don't know, 1.11. Okay, this is our margin of error. Okay, so remember, to find the lower and upper bound for our confidence interval, it's going to be our sample mean minus the margin of error, and the upper bound will be our sample mean plus that margin of error that we just found. Okay, so our sample mean is 66.47 minus 1.11, and then the upper bound will be 66.47 plus 1.11. Okay, and let's see what this is going to give us. I'll subtract 1.11 first. That's my lower bound. So 65 point, whoops. $65.36, that's my lower bound, and then my upper bound will be very similar. I'll just be adding that margin of error. And we get 67.58 inches, okay? And this is probably what was obtained from above. Let's go back and look. Well, the 67.58 and 65.36, is that what we got? Yeah, it is, okay? So this is the confidence interval. Now, as far as interpreting our results, you could just say, I'm 95% confident that the true population mean would be within this interval here. But more technically, you would say that 95% of the time, if I take a sample, 95% of the time, that sample statistic will actually fall within this range, okay? So, anyway, now what I want to do is show you how you can find these confidence intervals using the calculator, okay? So guys, all this arithmetic that I just did, you don't actually have to do that. The calculator will construct a confidence interval for you. You just tell it the level of confidence, you tell it what sigma is, the size of the sample, and what the sample mean is, and it'll do all this work for you. It'll calculate the margin of error, and then it'll subtract and add it to the sample mean to come up with your confidence interval. So let's do the same one with the calculator. Now with the calculator, you're going to come over here to Stat. You're going to come over here, scroll to the right to where it says Tests, and you're going to go down to number 7 where it says Z interval. So Z interval means we're using the standard normal distribution to come up with that critical value of Z. So you just hit Enter, and you're going to use Stats. Make sure Stats is highlighted, okay? Because we're using the statistics. We're not actually looking at the raw data. Okay, and then you come in here and you put in whatever sigma is. In this case, it was, I believe, 3.11. And then, yeah, 3.11. Then you type in whatever your sample mean is, so 66.47. And then the size of your sample, n, which is 30 in our case. And then our confidence level, which is 95%. Then you just hit calculate. Now, if you've got one of the older calculators, guys, you should still be able to do it, but you'd have to put these inside parentheses in this order, I believe. Okay. But anyway, look here, what it gives us. This is the interval right here, 65.36 all the way to 67.58, and that's exactly what we got. Okay, so that's pretty nice, isn't it? And that's actually what I'm going to use for the most part from here on out. So if you look at number 5 here, it says, repeat the previous problem with confidence intervals of 99% and 90%. And then what can we say about the width of the interval as the level of confidence increases? Well, let's try this. The nice thing about using the calculator here, guys, is that you just have to go back and change that confidence level. Okay, so let's do 99% first. So 0.99. I'm going to calculate, and look at this. This interval is actually a little bit wider than the previous interval. And I'm going to write down in here that I'm using the z interval function in our calculator. And so for when c is equal to 0.99, in our interval, our lower bound is, I'm going to round this to 2 decimal places, 65.01. And then our upper bound is 67.93 inches, okay? And then let's do the same thing over here for a 90% confidence interval. And my guess is that this one would be narrower. Oops, let me go over to tests, go down to z interval again. And let's change this level of confidence to 90%, 0.90. Hit enter. And this one is, in fact, narrower than the 95% confidence interval. Okay? So, really what's going on here, as we make that interval narrower, then we cannot be as certain, and so we're losing a degree of certainty or a degree of confidence. We're losing confidence, essentially. Okay, so this one goes from 65.54 all the way to the upper bound would be 67.40. Okay, so you can see that this one here is actually narrower than the 95% confidence interval. And so the greater the confidence, the wider the interval gets, right? It has to, because to be 99% certain, or such that 99% of the time the sample statistic falls within that interval, you have to have a wider interval for that to happen 99% of the time. So, all right, well, let's keep going here. It says use the confidence interval to find the margin of error in the sample mean. So here we're sort of going in reverse, because what they're giving us is an actual confidence interval. And we can work backwards, guys, and figure out what the sample mean actually was and what the margin of error was, okay? If you remember me saying earlier, in your confidence interval, the mean is always right in the center. It's the subtracting the margin of error and adding the margin of error, that's what gives you the lower and upper bound, okay? So what I would do, to figure out what value is right in the middle of these two, you need to average them. 0.424 plus 0.520. And if you divide that by 2, that'll give you the value that's right in the center of that interval, and that will be the sample mean. Okay, so if I do this, 0.424 plus 0.520. Hit enter. I'm going to divide that by 2. So that's the value that's right in the middle, 0.472. Okay, so X bar is that middle value, 0.472. Now, to figure out what the margin of error is, you can do it one of two ways. You can take your upper bound and subtract sample mean from it, or you can take the sample mean and subtract from it the lower bound. Those distances are going to be the same, so it doesn't really matter how you do it. If I take the upper bound and subtract my midpoint, which is the sample mean, that will give me the margin of error. Well, I'm just going to go ahead and do this. So 0.520 minus the 0.472, and we get 0.048. Okay, so this is the margin of error. All right. All right, well, let's keep going. Let's do number 7. We can do this one in the calculator. It says, a random sample of 55 home theater systems has a mean price of $134. That seems like a relatively inexpensive home theater system. Assume the population standard deviation is $16.10. And then we want to construct a 90% confidence interval for the population mean. Okay, so let's put in here what we know. We want C to be 90%. We know N is 55. That's the size of the sample. We know sigma is, with a standard deviation, $16.10. And then we know X bar, the mean price. It's $134. Okay. So we'll just plug all these into our calculator, unless you guys want to do it the long way by hand, which is fine. Okay, so I'm still using the statistics. My standard deviation now is $16.10. My sample mean is $134. The size of my sample is 55, and I want a 90% confidence interval, and that's actually what we already have in here. I'm just going to go to calculate. Whoops. Let me try that. Oh, wait a minute. Yeah, let's do that again. Accidentally clicked enter before I was finished. There we go. Okay. Oops. Here we go. Okay, so the lower bound is 130.43 dollars technically, and then the upper bound is $137.50. 57 cents. Okay. Now notice this is a relatively narrow confidence interval, okay, given the standard deviation and what the mean is. And that's because 90% confidence interval isn't all that stringent, I guess I should say. But anyway, that is your confidence interval, okay? All right, now the last thing we're going to talk about, guys, is let's say that we want to take a sample and we want our sample statistic, we want to be, 99% or 95% confident that our sample statistic is within a certain range, okay? And so how do we do that? Well, we can use a larger value of n. We can increase our sample size. Increasing our sample size, as you increase your sample size, it gets closer to the population, right? Because it increases the number and it starts to reflect the population more. So, anyway, if we look here, as the level of confidence increases, the confidence interval widens. As the confidence interval widens, the precision of the estimate decreases. So one way to improve the precision of an estimate without decreasing the level of confidence would be to increase the sample size. Okay, so to find the sample size necessary for a certain level of precision, we can manipulate the formula for the margin of error to get a new formula for the sample size. So essentially what we're doing here, guys, is we're taking that formula for the margin of error and we're solving it for n, because n represents the sample size. So what you do is you multiply both sides by the square root of n. That takes you to this point. And then you divide both sides by e, and then you square both sides to get n by itself. And this formula right here will tell you how big a sample you need to have such that you ensure a certain margin of error. So if if you're doing presidential polling and you don't want your margin of error to be more than 1 or 2%, then you can figure out how large of a sample you need to take. And it's probably going to be a fairly large sample, because normally those have a pretty large margin of error. All right, so we're going to be using this formula right here, guys. So it says, find the minimum sample size needed to estimate mu for the given values of C, sigma, and capital E, so the margin of error. So here, we only want the margin of error to be 1. And the standard deviation of the population is 8.7, and we want to have a 95% confidence interval. Okay, so in other words, what this confidence interval would look like, the lower bound would be 2 below the upper bound, and the mean would be right there in the middle. Okay, because the margin of error is 1. So 1 less than the mean plus 1 more than the mean would be a difference of just 2 in that entire interval. All right, well, let's go ahead and do this real quick. So I'm just going to use this previous formula right here. So n is equal to z sub c. So again, we still are going to need to know that critical value. So this is a z-score associated with a 95% confidence interval, times sigma over capital E, or the margin of error, and all of this is squared. Okay. All right, well, we know what z is. We've used it several times, right? It's 1.96 times sigma, which is 8.7, divided by, we only want to have a margin of error of 1, and then we're going to square all this. And that would tell us what our minimum sample size needs to be, such that our margin of error in our confidence interval is no more than 1. All right, so I'm going to plug this into the calculator. So you could do it like this, guys. You could just say 1.96 times 8.7, divide by whatever you have down there. In this case, it's just 1, so it's not going to change anything, and then square it. And so I end up getting 290.7. Well, you can't have 0.7 of a person, so you're going to have to round up. So this would be 291, okay? Our sample size would need to consist of at least 291 members to ensure that our margin of error stays this low. Now, as our sample size increases, our margin of error would decrease, and vice versa, okay? All right, and then we've got this last one, okay? Number 9, I think this one's kind of an interesting one. It says a soccer ball manufacturer wants to estimate the mean circumference of soccer balls within 0.14 of an inch. Okay, so basically this is kind of like your margin of error right here. We don't want the circumference to be more than this. So it says determine the minimum sample size required to construct a 99% confidence interval for the population mean and assume the population standard deviation is 0.6 inches. So I'm going to go ahead and write down our parameters here. For this one, we want a 99% confidence interval, and our population standard deviation is 0.6 inches, and let's see, our margin of error is 0.14 of an inch. Okay, how about that? And so if I use that same formula from above, we want 99% and it's going to equal our z-score times sigma divided by the margin of error and all of this squared. Okay, so 99% confidence interval, what is that critical value? Well, if you come back up here to your chart, I've got it in here. So we want to use this z-score, 2.575. Okay, so 2.575 times our standard deviation, which is 0.6 inches, divided by our margin of error, which we want to be within 0.14 of an inch, and we're going to square all of this. And this will give us our minimum sample size. Okay, so I'll go ahead and divide by 0.14. and then I will square it. Okay. All right, so we always round up here, so we're going to say 122. Okay, so we would actually have to measure or sample 122 of these soccer balls. That's how big our sample size would need to be, such that we could be assured that the true circumference of all the soccer balls that this manufacturer puts out is no farther than 0.14 inches away from our sample mean. All right, and then part B, it says the sample mean is 26.8 inches, and with a sample size of 133, a 99% level of confidence, and a population standard deviation of 0.6 inches, does it seem possible that the population mean could be less than 26.9? Okay. Well, for us to really answer this question, guys, we need to construct a confidence interval. Okay. And so to do that, I'm going to use my calculator again. the sample mean, well, let's just go get, our z-interval function, and we'll be using statistics. Our standard deviation is 0.6, or 0.6 of an inch. Our mean, the sample mean, is 26.8 inches. This is the circumference, okay, so the distance around the soccer ball. And then our sample size is 133, and then we're talking about a 99% confidence interval. Okay, so let's see what this interval is. Let's go to the nearest hundredths place. So 26.67 would be the lower bound, and then the upper bound is going to be 26.93. Okay, so then the question says, does it seem possible that the population mean could be less than 26.9? Well, I would say yes, because 26.9 is a little bit less than this upper bound. So it's actually within this interval, and anything less than 26.9, quite a few values would still be within this interval, okay? Because the difference between 26.9 and the lower bound of this interval is actually quite wide here, okay? So I would say definitely yes. In fact, guys, most of the interval is below 26.9. This is the same as 26.90, remember, okay? So this is real close to the actual upper bound. So you have everything to this lower bound within that interval. So it does seem possible that the population mean could actually be less than 26.9. Yeah, let me say one other thing. Because 26.9 is at the upper end of this interval. So chances are the true mean may be somewhere in the middle. But anyway, all right, guys, well, that's all of section 6.1. I made it in under an hour. So in 6.2, we'll be doing something very similar. We'll still be constructing confidence intervals, but we're going to be constructing them without actually knowing the population standard deviation. We're going to use the sample standard deviation as a substitute. And because of that, we lose some certainty. It actually causes our confidence intervals to become wider, and we end up having to use another distribution called a t-distribution, which is sort of like the standard normal distribution, except it's a lot wider. Okay, to account for that extra level of uncertainty, okay? So anyway, I'll see you there in 6.2.